So it's a pleasure to be here. I'd like to thank Professor Andy Yao and Han for organizing this faculty summit. I am going to talk about computational thinking in the sciences and beyond, given that the theme of this faculty summit is computing and sciences. Some of the comments I'm going to be making, some of you who were here 2 years ago will have heard them already, but I'm going to use Microsoft Research examples to populate my stories on how computational thinking has already influenced the research agenda of many science disciplines. I will also update you on some of the educational efforts that have been going around the world, including in China, on computational thinking, especially in the K through 12 space, but also at the college level. And I'm sure those kinds of updates will interest this particular audience. So I'm going to start with my grand vision. And my grand vision is that computational thinking will be a fundamental skill used by everyone in the world by the middle of the 21st century. And by fundamental skill, I mean as fundamental as reading, writing, and arithmetic. So wouldn't it be wonderful if we imagined every child learning computer science or computing in their K through 12 education? Of course, this is an incestuous vision in that computing and computers will enable the spread of computational thinking. Now, this vision has certain implications with respect to the research agenda of many different disciplines, and that's where I'm going to focus on the science disciplines today, but computational thinking has already influenced not just the sciences and engineering fields, but even beyond the liberal arts, humanities, the social sciences, economics, and so on. But this vision also has implications with respect to education. And because you are faculty at many universities and colleges in the Asia-Pacific region, I'm sure this vision is of interest to you in terms of how it will affect the curricula on your campuses and the K through 12 curricula in your countries. So I argue that already at the graduate level, computational thinking has pervaded in the ways in which graduate students are trained for the future. I think the challenge for us in society is, what does this vision of mine imply for the K through 12 education space? I wrote a 3-page article called Computational Thinking in 2006. It's a very easy read. It's a little poetic, but it's one of those articles that you read just before you go to bed to just kind of a light reading. And it is the article that perhaps has helped me spread my vision. And so for those of you who have read it and have argued for it, thank you for that. Okay, so in the article I talk about, I don't really define computational thinking. I say computational thinking is an approach to problem solving, building systems, and understanding human behavior using concepts from computer science. And of course, since that article, I've been hounded by everyone, to come up with a formal definition of computational thinking. And I think that's really difficult to do. This is the closest I've come up with, and I've had help from the community in trying to come up with a definition that all of us in computer science can understand. It still doesn't help people outside of computer science, unfortunately. But I wanted to really focus on the thought processes. Computational thinking is what happens in your head. It's the first thing that happens in your head that then gets translated into something that a machine might be able to execute, or a human might be able to execute. So computational thinking, first and foremost, are the thought processes involved in first formulating a problem and solving it. And this is the problem-solving part of computational thinking. Computational thinking is an approach to problem solving. But in problem solving, especially in computer science, just formulating the problem is a step forward. And so part of what I mean by thought processes involved in formulating a problem and expressing its solution is it's two parts of problem solving. One is formulating the problem, and the other is solving it. And then I say expressing a solution, because in computer science, we pay a lot of attention to the ways in which we express the solution. In fact, you can argue that many of the designs of many of the programming languages are different ways to express our solutions. Some languages are better at expressing certain kinds of solutions than other languages. Some languages are meant to express higher level solutions than lower level solutions, and so on and so forth. So expression is quite important. And then in such a way that a computer, and I'm very careful to say a computer can be a human or a machine. And in fact, in this day and age, a computer can be a network of humans and machines working together to solve a problem that neither can solve alone. So I'm very careful to include humans in a computer. And then can effectively carry out. The word effectively, of course, is critical here. It's not it is part of what is inherent to why it's computational thinking, and not just mathematical thinking, for instance. So I'd like to talk about computational thinking philosophically as actually complementing and combining mathematical and engineering thinking. Computational thinking certainly draws on mathematics as its foundations, because mathematics is the foundations of computer science, from the theoretical aspects of computer science. But in computer science, unlike in mathematics, we are actually constrained by the physics of the underlying machine that's going to effectively carry out the solution. Whether that machine is a machine that we're familiar with, like a laptop or a mobile device, or whether the machine is a human, and in fact, it's research still to understand the limitations, the computational limitations of a human solving problems. That's partly part of the whole quest in artificial intelligence, for instance. But unlike in mathematics, we can't very easily say for all x, p of x, because usually we are constrained, if we're especially talking about this kind of machine, we can't, we end up hitting against the limits of what that x is in terms of representation. Computational thinking also draws on engineering, since our systems interact with the real world. So any of our computing devices, any of the software that we write, in the end is communicating, interacting with either the physical world or a human being. And so all of our technology interacts with the real world. So it's like any engineered system, like a bridge or a building or any physical engineered system. It interacts with the real world. And so we have to keep in mind how a system that we build in computer science interacts with the real world. But the beauty of computer science or the secret weapon of computer science, in contrast to other engineering disciplines, is software. Software really is something special to computer science. And it's in software that we can design worlds that defy the laws of physics and defy the laws of nature. And so it's in software that we can build worlds that let us express how whatever we can imagine. So we are only limited by our imagination in the kinds of systems, in the kinds of worlds that we can build in computer science. So that's why, this is all philosophical, but that's why I like to think about computational thinking as complementing and combining mathematical and engineering thinking. When I talk about computational thinking, I really do mean those thought processes, the ideas, the concepts, the abstractions that computer scientists use on a routine basis. I'm not so focused on the artifacts that manifest those abstractions. So it's not just the software and the hardware. that touch our daily lives, but it's an approach to living, an approach to problem solving. And I do think that it is for everyone, everywhere. Just to be a little more concrete, I'm listing here some sample classes of computational concepts. And I'm listing these only to say not that every child has to learn all of these, but I think every child can learn some of these. And I think what's out on the open right now is to figure out collectively as a community what does make sense to teach what concept when. And the reason I list these kinds of concepts, which should be familiar to all of you, is to contrast what I mean by computational thinking and computer literacy. So there are many courses out there that teach how to use Word and Excel and PowerPoint and how to use search engines like Google or Bing. I'm not talking about that at all. I'm also using the term computational thinking to contrast what I mean with computer programming. Computer programming, of course, is a skill that all computer scientists learn and use routinely. But I'm saying that much beyond computer programming, there's more that computer scientists have to add to the thinking skills, to the reasoning ability, to the logical analysis that we in computer science do. And I especially don't mean, a course, for instance, that you typically find on a college campus offered to freshmen that's called, Introduction to Your Favorite Programming Language 101. That changes from year to year. It changes from decade to decade as programming languages change. And there's more to computer science than teaching just computer programming. So what I want to do is take a step back and look at, from the research perspective, how computational thinking has already influenced many different disciplines. And in the spirit of the theme of this faculty summit, I'm going to focus on the sciences and give you 4 different examples, 2 from biology and 2 from the social and economic sciences. So I already gave away my usual question, but what I'm going to do is look at one discipline and argue that many different computational methods have already influenced the thinking in that discipline. And at this point, normally I say, what one discipline might that be, but I already gave that away. So it's biology. And I think for me, when it was the sequencing of the human genome, I think it was that breakthrough that when biologists sort of sat up and said, hey, maybe computer scientists have something to bear on the way I, as a biologist, can solve problems in biology. And it was the algorithm that really expedited the sequencing of the human genome. And of course, the architecture of the arrays of machines that helped as well. But in all these examples in biology, these different computational methods, processes, languages, techniques, and tools have one commonality, and that is these methods, languages, tools, and techniques all are useful for explaining the dynamics of processes. And for us in computer science, we use these kinds of tools, techniques, and methods to explain computational processes and how they interact, whether they're concurrent processes in an operating system or processes in a distributed system or fault-tolerant kinds of systems where you have to worry about reliability. All sorts of different tools, techniques, languages, models that we have invented in computer science all are ways to understand the dynamic interactions between and among processes. So for us, this is kind of bread and butter. But it so happens that these kinds of methods, tools, techniques, and languages can be used to explain the dynamics of biological processes. And that's the aha, or that's the dare, or that's the hope. So what I want to do is explain in one example from some work done at Microsoft Research on stem cell prediction. And this is very recent work just published in Science of this summer. And the idea is to do stem cell prediction. So the problem is a biological problem. And let me first explain it and then show you how a computational tool and method or thinking came to bear to help understand stem cell prediction. So this starts with embryonic stem cells. And embryonic stem cells have two properties that make them special. The first is that they're self-renewing, which means they divide indefinitely. So there's always plenty of them. And that's pretty amazing. The second is this notion of pluripotency, which means they can generate all adult cell types. So a particular stem cell can eventually evolve into a brain cell or a lung cell or a kidney cell. So we understand that. We don't understand how it happens, but we understand that happens. And interestingly enough, we also know that if you take an adult cell, we can actually convert it into a stem cell. So this gives us the hope of taking an adult cell, converting it into a stem cell, and if we can only make that stem cell evolve into a kind of cell that we want, then we have the hope of addressing a lot of different diseases and so on. So this is the grand vision of why one would really want to understand the behavior of embryonic stem cells. So it turns out that the biologists already know that embryonic stem cell reacts to certain kinds of signals. In fact, LIF, chiron, and PD, two out of the three signals will cause some reaction in the stem cell in terms of the genes and the expression of those genes. And so what we can do is we can look at the different combinations of 2 out of 3 signals and see how each of the genes in the stem cell react. And then what we can do is we basically, from what we see in the experimental observations, we can build this graph where these blue nodes are genes, and these black nodes are the signals. And a black line shows a positive interaction between the genes, and a red line shows an inhibitory reaction. And it turns out that if you consider all the different nodes and lines and signaling signals as inputs, you have 10 to the 43 possible state machines. And when you talk to computer scientists, they're not daunted by 10 to the 43 state machines. Because we have, for instance, verification techniques like model checking and SAT solvers and so on that can easily handle large state spaces. So for computer scientists, this is a great example of how can we actually reduce the search space or reduce the number of plausible state machines. If all we had to do was find some constraints to reduce the number of possible state machines to just the plausible ones, then we actually have made some progress. And it turns out that at Microsoft Research, we built and invented a tool called Z3 or Z3, which is the best constraint solver in the world. And the computational biologists at Microsoft Research knew about this Z3 tool that our programming languages and verification researchers built for completely other reasons, and used Z3 to constrain the 10 to the 43 possible state machines into the plausible ones. And what they used for their constraints were actually observations from real experiments that the biologists have done over the years. So you go through all the literature in biology, look at the experimental observations, and use those to constrain what state machines, if you will, are really plausible. And so in that's what they were able to do. And so the set of possible models was constrained by experimentally observed behaviors. And this set was used to make a large number of predictions, non-intuitive predictions, of the response of the network to genetic perturbations. And then these predictions, which were done purely on these, state machines, were experimentally validated with over 70% accuracy, which is unprecedented in this particular area of biology. Moreover, what they were able to show is that this state machine, if you will, on the right, is like the kernel, the minimal genes and interactions given the signals that I mentioned before that show up in all the plausible models. And this was the new discovery in biology. And this was what was part of that Nature paper. So they're using off-the-shelf computational techniques and tools to make new discoveries in biology. And so this is pretty exciting to me. And especially when I am from the community, research community, that plays with tools like model checkers and theorem provers and constraint solvers. And we hardly, invent these things thinking that we're going to discover biology in 20 years. So it's pretty exciting for me to see this application of a constraint solver in such a profound way to biology. Okay. So I argued, and just with one example, that one discipline, biology, has been influenced and is influencing many, has been influenced by many computational methods, tools, techniques, and languages. But let me flip it around and say, and ask you, what one computational method has been used by many different disciplines? This is the interactive part of the talk. Don't be shy. Oh, you're so shy. Machine learning. So you all have heard of machine learning, I'm sure. Machine learning to me, and this is already years ago, has transformed the field of statistics. This is certainly true at Carnegie Mellon, where we see the machine learning department as part of the School of Computer Science, and the machine learning department is made up of faculty from the computer science department and faculty from the statistics department. In fact, they should be called the Department of Statistical Machine Learning. And I can tell other stories about how I feel, why I feel machine learning has transformed statistics, but I'm not going to focus on that. Machine learning in the sciences has already been able to be used in astronomy to make new discoveries like brown dwarfs and fossil galaxies. It's used in medicine to detect tumors in mammograms. It's used in meteorology for understanding tornado formation. It's used in the neurosciences where you apply it to a multitude of fMRI scans to understand what part of your brain lights up when you're looking at a verb versus looking at a noun. The story I wanted to tell is also from Microsoft Research, a different science group, where the aha, it's also a biology story, so this is machine learning and biology, where the aha is that we have been using machine learning for many years to fight spam. And in fact, this very research group I'm talking about invented a machine learning algorithm originally to fight spam. It turns out that the computational thinking idea here is, well, spammers mute messages to work around filters. So the solution to that is go after the weak link. Now here's the aha. Can we use machine learning to fight HIV in the way that we can fight spam? And the analogy is that HIV mutates to avoid attack by the immune system. So the solution is go after the weak link. And what's so amazing, and I'm going to talk a little bit more about this, is that the techniques that I'm going to talk about actually are able, and right now I'm talking about ongoing work in Microsoft Research, are able to understand vulnerable regions, the weak links in HIV. So the strategy is to identify what are called vulnerable regions in HIV. And then if we can identify these vulnerable regions, we can create a vaccine that teaches the immune system to target just those regions. And the reason this is important is as follows. This HIV protein is made up basically of a string of amino acids that fold over each other in 3D. And what happens when the immune system attacks this protein, the protein is robust in many places to attack, it just mutates, and it still retains the functionality that is so destructive to humans. And so you poke it, and it mutates, it's still bad for humans. But there are places that perhaps, for instance, in this place I'm showing here where the two loops intersect or are next to each other, where that's called a vulnerable region because that's where if the immune system attacks just at that point, the HIV protein will not mutate in a way that the immune system, it will not mutate so that it will weaken it will weaken the functionality of destroying the human. So then how do we find these vulnerable regions? That's the question. And what the researchers at Microsoft did in collaboration with researchers at Harvard is to realize that in the world there are some people who are called controllers who have the HIV virus but don't get sick. And then there are the normal people who have the HIV virus but do get sick. And so what you can do is you can look for differences between where the immune systems of the controllers attack HIV versus where the immune systems of the normal people attack HIV. And you can use lots and lots of data to help you look for these differences. And what these researchers did was to actually use pretty much machine learning techniques to identify these vulnerable regions, and they were able to identify 8 regions of HIV proteins where controllers were much more likely to attack. So that was step 1, and that was tantalizing to the researchers. And in fact, they went further to find more vulnerable regions. They used in silico prediction under certain assumptions, and using the protein database that's been generated by the biology community to run high energy simulations, and then using this fold-X algorithm, we're able to actually identify many more regions as noted here. So these regions here are also new candidates of vulnerable regions. So the idea then is, going back to the computational thinking, is that finding the weak link in spam was the metaphor for finding the weak link in HIV. Okay, so machine learning is everywhere, not just in The sciences, the machine learning is of course used for detecting credit card spam. It's used on Wall Street for good or bad. It's used in supermarkets where you get coupons when you check out based on your previous buying patterns. It's used in all these recommendation systems that you might be familiar with when you're going shopping or watching movies. And it's even used in sports. So right now there are people who are actually getting funding from professional sports agencies to use machine learning and data analytics to understand how best to train and coach their athletes. Computational thinking, of course, goes beyond just the sciences, even though that's the theme of this faculty summit. And I just wanted to hint at a couple of those examples. Computational thinking in the sciences, in chemistry, physics, and the geosciences, and in math and engineering. But what I really wanted to get to is computational thinking beyond the sciences, where it's affecting disciplines that are more social, behavioral in nature. So in economics, for instance, in law, and in healthcare. And the two examples I want to give, again, for Microsoft Research have to do with computational thinking in economics and computational thinking in the social sciences. So the one in economics has to do with polling. So here I'm going to talk about the difference between what's called representative polling and non-representative polling. For instance, in the United States, when we have a presidential election, normally professional polling companies use what's called representative sampling, where you take a representation, or you take a sampling of the US population, hoping that you're getting a representative sample, and to be able to predict the winner of the election. And that's a billion-dollar business. The 2012 presidential election cost the professional polling companies over $6 billion over the course of 2 years. And so the question is, does this representative sampling polling method actually give you a good prediction of who's going to win the election? And some researchers at Microsoft Research took a completely different approach. It's cheaper, faster, and more accurate. And counterintuitively, it's based on this notion of non-representative sampling. And here, they actually polled Xbox users over a period of 45 days, got many, many more respondents than you would typically get in a representative sampling. And for each respondent, they were able to collect information about the age, the gender, the race, the education level, and so on. And what they were able to do is collect a lot of data. And let me show you the data first, because collecting the data is just the first step. So here's the election in 2012 was Obama versus Romney. And you'll notice that this dotted line, that straight dotted line that goes across, is the final election outcome, where Obama won. And the professional pollers, over time, in this 45-day period, you can see that that's that thick dotted line. And they underestimated the final election outcome. And the raw Xbox data that was collected from the players of Xbox, that's the raw data, this red line. And actually it doesn't look very good, does it? And the reason is, of course, this is just data. What you really need to do is analyze the data appropriately so that it is indicative of how people actually will vote. And the way they do this is through a technique called post-stratification. So the idea is to take an individual, and for instance, if the individual in a representative poll might say a man from New York, so this is a man from New York. But in this particular post-stratification, what you do is you consider this man from New York, you label the this individual is a man, so, and then also a person from New York. And so then you have many more bins in which you can correlate the different combinations of men and age and gender and so on, and then aggregate the properties to come up with what would be a representation of the voters in an election. And so it is through that post-stratification process that you can accommodate the fact that your original input is based on a non-representative sampling of the population. And by the way, you should realize that most, like 95% of Xbox users are male, and they're between the age of like 19 and 29. So it is very much a non-representative sampling. But there were enough women over 65 that they could actually get some information, get some signal out of those particular respondents. And so after you do this kind of data analysis based on the collection, based on the data collection, then here's what they were able to predict. And so the corrected Xbox, that's the post-stratification using also multi-regression and so on, line is the one in the thick red line here. And you can see towards the end of, near the voting date, they were pretty much spot on in who was going to win. And they did better than the $6.4 billion worth of polling that had occurred for 2 years before the election date. This was, of course, just one example of using this particular technique for predicting who's going to win the presidential election, and that many other examples since then this team has done, and for instance in the World Cup, in the Oscar ceremonies, that's the Hollywood awards that are given out every year, and so on. And right now, if you're very interested in this, you can go to what's called the Microsoft Prediction Lab, and that's actually a website. And you yourself can participate in these kinds of polls and surveys. The last point I wanted to make mention about this kind of work is it's also very important to be clear about what kind of question you actually ask the people you're polling. So it turns out that, for instance, you get a better prediction if you ask the question, instead of asking the question, who are you going to vote for? If you ask the question, who do you think will win? And that's why this particular team also uses data not just by asking questions of individuals, but looking at data from Twitter, data from betting pools, and so on. So in fact, it's multiple data sources that this Microsoft Prediction Lab uses in order to do their kinds of predictions. Okay, so that was computational thinking in economics. Computational thinking, as I've mentioned, beyond the sciences, also has had influence in archaeology. There was an e-heritage project that started in Microsoft Research Asia here many years ago, and I've still ongoing. There's many programs now in the United States on computational journalism, master's level programs, digital journalism. In fact, at Columbia University, the School of Journalism just hired a couple new faculty members, and they were PhDs in computer science. In the humanities, a lot of it is based on big data and digging into data and understanding patterns across different disciplines, but also just within a discipline, in history and literature and so on. The example I want to give you is again from Microsoft Research, having to do with the combination of computational computer science and anthropology and learning about crowd workers. So in this work, the researcher for Microsoft Research and her colleagues use digital studies to basically produce graphs, nodes, and relationships in the nodes, and then uses anthropology to understand the kinds of relations on the kinds of nodes. And in this particular work that I'm going to describe to you, what they wanted to study was what is the economic model, the incentive and reward structure for crowd workers, and what they concluded was that the economic model for understanding crowd workers is not the perfect competition model, which is what most of our economy is based on. In the perfect competition model, there's a law called law of one pricing, where equal pay is given for equal jobs. So if you do the same job, you get the same pay. It turns out that in this study, that the perfect competition model doesn't hold. In fact, what's called the imperfect competition model holds, where the law of one pricing does not hold. In this particular case, different Amazon mechanical turkers might be doing the same job, but actually get paid differently. And so it was in studying and mapping the crowd and looking at some of the commonalities of where the crowd workers are, for instance, internet access, and so on, that allowed them to hypothesize that the imperfect competition model better explains the economic model for how crowd working works. And then the study I'm citing goes on to suggest different policy recommendations for addressing this imperfect competition. So now let me turn to education. And I wanted to say that, I said this already, that at the undergraduate level, at the graduate level, we're already seeing a lot of progress in computational thinking. I think the real challenge is the K through 12 level. And we talked, Han mentioned earlier about the pipeline going into the earlier stages of the pipeline. I think if we can do that, we'll see a very different society in the future. So I've asked the question of the computer science community, what is an effective way of learning or teaching computational thinking by or to the K through 12 space? And I think my analogy is to mathematics. Somehow, by the time you're 5 years old in kindergarten, you have a sense of number. And by the time you're 12 years old or in 7th grade, you have mathematical sophistication enough to learn algebra. And by the time you're 18 years old or in 12th grade, you have the concepts behind you and the mathematical sophistication to learn calculus. So what's the analogy in computer science? When is the right time to learn or teach recursion? Or maybe there are these inherent concepts that we're born with, innate concepts that we're born with. Those are actually research questions. So, and then there's, of course, the challenge of how do we best integrate the computer, the device, in teaching these concepts. And one of the concerns I have with MOOCs is that we're just throwing technology at something. How do we know that this is actually improving and enhancing our learning? Okay, but what I wanted to do is, well, here's my short example of computational thinking in daily life. So, and then I'll talk about the progress we've made around the world in education. So here is me this is actually me at the National Science Foundation cafeteria on my second day. And what I do is I get a cup, and then I put some milk in it, and then some coffee, and then I put some sugar in, and then I put a lid on, get a napkin, and leave. So, as a computer scientist, I look at this coffee station and I say, well, what's wrong with this coffee station? What's wrong with this coffee station? Let me give you a hint. It's even worse when there's like someone in your way. So as a computer scientist, what do I think, or what do you think? What's the concept that's going to help me make this coffee station more efficient? Well, I think pipelining. And then I actually think, oh, well, what are the minimum stations I need to move to affect a pipeline? Is actually the most efficient pipeline, and blah, 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 blah. But of course, I'm just at the cafeteria. So in fact, if you think about it, you just need to move the lids over, and it's not the most efficient pipeline, but it certainly helps. So this is just an example of computational thinking in daily life. It's not that there's a hard, difficult problem that you're trying to solve, but it's a way that you bring in the concepts you've learned in computer science to approaching daily routine activities. Okay, so now let me talk about the efforts in the United States, in the United Kingdom, and China having to do with computational thinking. And in the United States, this is a busy slide, but let me just focus on two efforts. The biggest effort that's happening in the United States is a revamping of the advanced placement computer science course that is offered to high school students. And this has been ongoing since about 2009. And the hope is that, the plan is that this new AP class in computer science is actually going to teach fundamental principles of computer science, not just programming in your favorite programming language. And the reason this is such an important leverage in the United States is that in the United States, to affect any change at the K through 12 level means actually going to 10,000 school districts one by one and trying to affect the change. Because in the United States, the public school system at the K through 12 level is completely decentralized. And so the one lever we have is these AP classes and the AP tests that high school students like to take in order to get college credit when they enter college. And so if we can capture that one point, that attention of theirs, then we can affect we have some amount of ability to change high school curriculum in a more in a simpler way than going to school district one by one. And so that's been ongoing. And at the same time, not only do you want this high school course to change, but you also need the freshman level college course to change, because you're supposed to be getting college credit for that course. And so fortunately, as this change in the advanced placement curricula has been ongoing, so have changes across many colleges and universities in the United States in terms of adding or changing a course at the freshman level specifically for non-majors, but often not even for majors as well. And it's basically computer science concepts for non-majors. And many classes now many campuses now are changing their freshman level course to be more about computational concepts and not computer programming. In fact, one of the most popular courses at Harvard University is exactly this course. Now part of that is due to the instructor, who's very popular, but the students do vote with their feet. So that is what's going on in the US. The kind of parallel efforts in changing the high school curriculum for computer science and the undergraduate freshman level curriculum, especially for non-majors. I'm really impressed with what the United Kingdom has done. And this started already in 2012. In January 2012, this report from the British Royal Society came out called Shut Down or Restart. And it acknowledged the importance of computational thinking, but more importantly, they already had in the UK a required computing course. And that required computing course was really about computing skills, learning Word and Excel and so on. So fortunately, there was already room in the K through 12 curriculum. And what has happened since 2012 is replacing the content of that required computing course with honest-to-goodness content about computer science. And so very, very excited about this. Computing at school in the UK is K through 12 in the US. There's an effort that started since 2012. It's really a grassroots effort, and I'm really proud to say that one of the persons behind this effort was a Microsoft researcher at Cambridge, Simon Peyton-Jones. And this fall, 2014, is the first rollout of a K through 12 curricula for that includes computational thinking, teaching computational thinking concepts at each grade level. So there's a spelled out curriculum for each level, and right now they're making it happen. And this is just for England now. So this is pretty, it's experimental, it's pretty exciting, it's pretty new, and we'll see what happens. But the UK was really, of all the countries around the world, was really the gutsy lead on this. So what about in other countries? Well, I wanted to really focus on what's happening in China. So I guess that's me on a boat after the faculty summit in Seattle, talking to Professor Guoliang Shen, who is the key influencer of computational thinking in China. And he was the one who started the first computer science fundamental course of computational thinking. And what has happened since then is, in 2012, the Chinese Ministry of Education, the MOE, announced a program to reform the computing fundamental courses focusing on computational thinking. And why this is important is, at the time, this particular course that was offered had a couple of problems. One was that in some places, what that course covered was trying to cover too much. It covered computer history, languages, operating systems. It's kind of throwing it all into one course, and people really didn't get a deep understanding of some of the concepts. In other variations of this course, it really was about teaching computer skills, like using Word and PowerPoint and Excel and so on. And so and many students would take that course and be really bored because they knew this stuff already, and they didn't understand the value of, they didn't get the appreciation of the depth of computer science as a field. So in any case, the other thing so this is happening right now, in just as I speak, with Microsoft Research Asia's participation. We and the MOE are jointly putting forward a program to sponsor 16 full computational thinking courses and 100 case studies. And the proposals are due pretty soon, or maybe they're in already, and 16 will be chosen. And so this really shows the lead of Microsoft Research Asia in helping revamp the college curriculum in China. And so the hope is to empower 7 million students with computational thinking ability through these CS fundamental courses. Okay, so I will stop there. My little 3-page article was translated into Chinese and into French, so you can actually read the article in Chinese if you want. So I will just help me spread the computational thinking. And help me make computational thinking commonplace. That's my plea to you. Thank you.